I'm going to concentrate on filters. Right, briefly explained, a filter allows you to remove unwanted frequencies, and it also allows you to keep certain frequencies. Which frequencies are removed and which ones are kept depends on the type of filter you use. We'll get onto these in a minute. But before we can list the different types of filters that Subtractor has and what they do, there are a few terms and definitions we need to cover. These are crucial and are used all the time, so it's important that you know what these terms are and what they mean. Let's start off with cutoff frequency. In Subtractor, the cutoff frequency is determined by this slider on both filters. Basically what the cutoff frequency is the point of frequency at which the filter begins to filter or block or cut out. The filter will lower the volume of the frequencies above or below the cutoff frequency depending on the type of filter used. This lowering of volume of frequencies is called attenuation. In the case of a low-pass filter, as we have selected here, the frequencies above the cutoff point are attenuated. In the case of a high-pass filter, like this one, it's the exact opposite. So basically what this means is that the frequencies in the example of the high-pass filter below the cutoff point are attenuated. So what you're going to hear are the frequencies above the cutoff point. The speed at which the filter attenuates is called the slope or gradient. So the speed at which the filter attenuates is called the slope or gradient. Another point to raise now is that you will often see values on the filter knobs that have 12 or 24 dB, as you do here. That basically means that each time the frequency doubles, the filter attenuates by 12 or 24 dBs, everything at that frequency. These are known as 2 or 4 pole filters. It's not important for you to understand about pole filters, etc. right now. And all you need to care about in terms of how they sound. The 24 dB will have a steeper roll-off curve, and the 12 dB will have a gentler roll-off curve. We'll come on to that later when we start using some real-life examples. Right, let's go through what each filter means then. So we'll start off with the low-pass filter. As we talked about this earlier, the filter attenuates the frequencies above the cutoff point and lets the frequencies below the cutoff point through. In other words, it allows the lower frequencies through and blocks the higher frequencies out. That's it. It's that simple. However, remember that the low pass is one mother of a filter. If used on a bass sound, it can give it more bottom, give it more deeper tones. If used on a pad sound, you can have the filter open and close or just sweep it. We'll come on to all these examples a little later on. Let's get on to the high pass filter. Now the high pass filter is the exact opposite of the low pass filter. This filter removes frequencies below the cutoff and lets through the frequencies above the cutoff. It's actually that simple. I personally like to use a high pass filter, particularly on pad sounds or sort of DX type of Rhodesy sounds. It really adds some sparkle. If you're into audio recording vocals, then the high pass filters always add a little more brightness to the vocals if you use them sensibly. Okay, let's get on to the next one now, which is the band pass. The band pass filter is a filter that attenuates frequencies below and above the cutoff and leaves the frequencies at the cutoff. It is in effect a low pass and a high pass together. Now, I know that sounds confusing, but think of it as this way, as if, imagine you had a whole frequency spectrum like this. And you basically wanted to get rid of everything below and everything above. So you want to get rid of lower frequencies and higher frequencies and just home in on this one narrow band of frequencies that you want to play with. That's what the bandpass does. Next one up, Subtractor calls it the notch filter. I call it the band reject filter. It's exactly the same thing. This is the exact opposite of the bandpass filter. It allows frequencies below and above the cutoff and attenuates the frequencies around the cutoff point. So basically, instead of the bandpass, which attenuated frequencies above and below and kept these frequencies, you're doing the exact opposite. You're getting rid of these ones and keeping the ones at the top and the bottom. Why is this so good? Well, it eliminates a narrow band of frequencies which are at the cutoff point. That in itself is a great tool. You can use this on all sounds and can have a distinct effect on a sound. Not only in terms of eliminating the frequencies that you want eliminated, but also in terms of creating a new flavor to a sound. When we come later to do some examples, you'll hear what a notch or a band reject does, so it'll make a lot more sense. Right, let's move on. We've now covered all the filter types. Let's move on to resonance. Most synthesizer manufacturers, and in the case of most analog synthesizers, the term resonance is used most commonly. Other manufacturers of synthesizers or software synthesizers might call it emphasis or Q. I'm sure you've seen the Q many times when you're using EQs, like the Waves plugins, etc., or any VST-based EQ or filter will invariably have an EQ, will have a Q factor. They don't often call it emphasis. It'll usually be resonance or Q. So if you boost the narrow band of frequencies at the cutoff point, i.e. the section right there, that is called resonance. In an analog synth, if you were to push the resonance all the way up to the top, you would get self-oscillation. This means that we'll generate an audible sine wave, a bit like whistling, even when receiving no input signal. Now right now I'm not pressing any keys on Subtractor, so it's not receiving an input signal, and I've moved the resonance all the way up and nothing's happening. You tend to find that it's really in terms of analog design that you will get this. Very cool way of understanding what resonance sounds like is to perform what we call a sweep. Yeah, that's another flash and funky term we programmers use to explain something really simple. Sweeping the filter means manually turning the resonance up, down, or clockwise, whatever, and select the waveform, select the cutoff point, and turn the resonance knob and listen to the results. As you're sweeping, the resonance goes through all the different frequency harmonics of the waveform and boosts them at the cutoff point. Again,